All right, now we're going to do a review for our second unit test, and it's chapters 4 through 6. All right. Um, Make sure we talked about physical and chemical properties, physical and chemical changes. So remember, if it's a physical change, you're just describing what something looks like. If it's a chemical change, you're describing how it changes into something else. Okay. So in here, orange, any color would be physical. You're describing it. Taste bitter, again, you're describing it. And we don't really use taste in the chemical lab, you guys. Ooh. Reacts with. Anytime you've seen reacts with, it doesn't matter what it says here. Okay. Acid, um, air, anything. If you see reacts with, you know that's a chemical. Okay. Dissolves in water. Some people think that's a chemical. Mm-mm. If you take salt and you dissolve it in water, if you evaporate the water, you got your salt back. So you're just saying how it can, change into a different form, but it's still the same substance. Okay. Is very hard. You're describing it. Density, describing it. Because remember, density tells you how close the little particles are. So you're just saying how close the little particles, how heavy it is. Okay, is a regular solid. Again, shape, that's physical. So on here, really, we only have, oops, reacts with acid. All the rest of them are physical. Okay, boils. Now, some people think that's a chemical change because when you boil water, the water disappears. No, it doesn't. It just changes to a form we can't see. It changes to a gas. But boiling, melting, any of those phase changes, those are all physical. Burns would definitely be chemical. Okay, because when you're done, you're going to have something different. Has luster, that means it's shiny. That's describing it, physical. Reacts, there's that magical word. If you see reacts with, that's chemical. Mass, length, any of those things, those are all physical. Produces a gas. If you produce a gas, that means you're going through a chemical change, okay? So if it bubbles or fizzes, that is a chemical change. And crystal shape, that'd be physical. You're describing it, okay? All right, now we said those are properties. Those are describing it. Physical and chemical changes, this is where something happens and you change form or whatever. And again, remember, a physical change would be like a change in phase, melting something, boiling something, that kind of stuff. It's still the same substance, and that's what you look for. If it's a chemical change, you got a new substance with new properties, okay? So like if it fizzes when added to water, fizzes means you're producing a gas, new substance, that's chemical. Cutting an apple in half, it's still an apple, okay? Now, if you let it sit out and the apple turns from white to brown, that would be chemical. It's actually rusting with the air, okay? Growing a tree. Growing is chemical, okay? Because you have to have like photosynthesis, you have to have all these chemical reactions going on for a tree to grow. So that would definitely be chemical. Iron rusting, chemical. Rust is not the same as iron. Any of you guys that have rusty vehicles, you know what I'm talking about. Because pretty soon you don't have rust anymore. Pretty soon you have little holes, and that really stinks. Okay, dissolving salt in water, the salt is still in there. Okay, so dissolving is a physical change. Boiling, metals. Okay, boiling, melting, freezing, those are all physical changes because you still have the same substance. If you bake bread, that's chemical. Any type of cooking, baking, whatever, because there's going to be a change. Okay, the yeast reacts and produces carbon dioxide, your bread rises and all that. That's a chemical. Gives off heat. If you give off heat, you're burning. So that has to be chemical. And evaporating, again, that's just a phase change. So that would be physical. Okay. All right. Specific heat, remember, is the heat lost or gained equals the specific heat times the mass times the change in temperature. Okay. So, and if we're doing specific heat, if we're looking for the specific heat and we know the amount of heat lost or gained, you take the amount of heat lost or gained divided by the mass divided by the change in the temperature. Okay. So what I did was I took 780. That's the heat that was absorbed. Here's my mass, 56. And then I took 79 minus 41 and I got 38. That's the change in temperature. So if I take 780 divided by 56 divided by 38, I'll get 0.367. This is a specific heat. I know this is some kind of metal because it's less than 1. Okay. If I'm trying to find the amount of energy, the amount of heat that's lost, absorbed, or gained, this, you just multiply everything. So you have the specific heat, you have the change in temperature, and you have the mass. So you're just going to take this times this times this. Okay. So, and those formulas are in your notes. All you have to do is plug in the numbers that you know. So if you just multiply them, what you'll end up getting is 153, sorry, 15,321.9 joules. That's how much energy is released when you have this 389 gram piece of metal and you heat it up 86 degrees. That's how much heat you're going to need to do that, okay? All right, who did the following? Wrote the atomic theory? Of course, the cool chemistry dude, John Dalton. Okay, discovered the electron. The guy with the cathode ray tube? Thomson. JJ, I don't even know. Maybe his name was John Jay, right? Discovered the neutron? That would be Ernst or Ernest, whichever way you say it. What did I say? Neutron. I'm going with the nucleus. Sorry. The neutron was Chadwick. The nucleus was Rutherford. Okay, so Rutherford was the one that did the gold foil where he passed beams through and they bounced back. And so if they bounced back, he knew there was a heavy metal. That was the nucleus. Chadwick was the one that said, hey, there's another particle in the nucleus besides a proton. There's these little particles. They don't have a charge, but they allow to add mass to it. Okay, so we got Dalton wrote the atomic theory, Thomson, electron, Chadwick, neutron, and the nucleus, which has the protons and the neutrons, was Rutherford. Okay, what is the atomic number of the following? You guys, all you have to do is look them up on the periodic table. Sodium is 11. Titanium is 22. So it's just the number on top there. This is the number of protons. Okay, so when I put a bunch of them in here, I don't know, whatever. But the atomic number, and that's the order they go in. They go from 1 to 118. They go in order, and that's the number of protons. Okay, the atomic mass, okay, is the number on the bottom. And we just round that, like sulfur is 32.06, 32. Thallium is 204. It's the number on the bottom. And remember, the atomic mass is the protons and the neutrons added together. And the reason why it's not whole numbers, remember we did the isotopes, the relative number of isotopes. Okay, so it's the number on the bottom. Okay, all right, and again, you just find these on the chart. The number on the bottom, that's the mass. Okay, so what is the positive particle? Well, proton. Okay, that's in the nucleus. The negative, electron. And remember, in an atom, they equal each other. They have to, because an atom doesn't have a charge. So if you have 240 protons, you need 240 electrons, okay? We can move the electrons around. We talked about ions, but in an atom, they equal each other, okay? The two particles found in the nucleus, and remember, the nucleus makes up the mass of the atom. So that would be the proton and the neutron. You add those together to get the mass. The electron is so small, we don't even figure it into the mass, okay? Okay, so atomic number is equal to the number of protons. Those two are always the same. If you change the number of protons, you have a different element. Okay, you can change the number of neutrons, you can change the number of electrons, but you can't change the number of protons. Okay, the particle that is transferred in ions, those are the electrons. The electrons are on the outside. They're hanging out here, so it's easier to move them around. Okay, and then we get ions. Okay, what two particles make up the mass? We already talked about that, the protons and the neutrons. You add those two guys together, they're in the nucleus, they make up the mass. Okay, and what's the name of a positive ion? Remember, you're positive, your cat is in trouble. Okay, positive ions would be your metals, because the metals give up their electrons and then they become positive. Okay, number of protons, electrons, and neutrons. Okay, so if you have Ca, calcium, and this is its mass 40, you'd look on the chart and you'd find out its atomic number is 20. So it has 20 protons and it has 20 electrons. Those would be the same. To get the neutrons, you take 40 minus 20. In this case, it would be 20 as well. So it has 20, 20, 20. That doesn't happen that often. It does with the smaller elements, but not so much with the big guys. Okay, gallium. Gallium is 70. So you look on your periodic table. I got to find my periodic table. And gallium's number is 31. So it has 31 protons, it has 31 electrons, and so I take 70 minus 31 to get 39, okay? So again, the protons and electrons equal the atomic number. That's the number on the chart, okay? To get this number, you take this number minus this number, and you get that number, okay? Because the atomic mass is made up of the protons and the neutrons, so if I know the total and I know protons, subtract them, I'll get the neutrons. Okay, and I have a bunch of these on here. You can practice those if you want. Okay, all right, isotopes. Remember, all elements have substances that they have more or less neutrons. The protons have to be the same, okay? But you can change the number of neutrons. So when we're trying to figure out the relative mass, which is the mass you find on the periodic table, we have to do all the isotopes. We have to take their mass times their relative abundance. So I would take 54 times, and again, you can't multiply by 6. It'd have to be 0.06 because you got to change this back to a decimal. So 54 times 0.06, 56 times 0.92, and 57 times 0.02. Okay, so when you multiply them, this one, and again, make sure you move that decimal over. You get this, you get this, and you get this. You add them together and you get 55.9 AMU. Look on the periodic table and see what iron is. It should be close to that number. If it's way off from that number, then you know you messed up. Okay, go back and look at your numbers. You probably didn't move your decimal over, but that's how you find the mass of isotopes. Okay, all right, and here's another one, same kind of deal. So you can go back and check on that, but it's how you find the mass of the isotopes. Okay, name the following. We spent a lot of time on this, and it's really important, you guys, because you gotta know how to name compounds. Okay, this is iron sulfide, I know that, but which iron is it? If I put a -2 here, I know sulfur is -2, so -2 times 3 is -6. So this side has to be +6. 6 divided by 2 is 3. So it'd be iron 3 sulfide. Okay, remember this number is not that number. They aren't the same. Okay, that's NH4 is ammonium. It's a polyatomic ion. How do I know there's a polyatomic ion? Well, look, 1, 2, 3 capital letters. I know it's in there. Find it. NH4 is ammonium. Cl is chloride. Okay, CaO, calcium. Okay, calcium is just calcium, and O is oxide. Okay, barium, and then hydroxide. OH is a polyatomic ion. I got 3 capital letters. Okay, this is another one. Copper can be 1 or 2. So which one is it? Sulfur. Sulfur is -2, so copper is +2. So it's copper 2, Cu2S. Okay. And then that one, 3 capital letters, potassium, and PO4 is phosphate. It's one of those polyatomic ions. So potassium phosphate. Okay. Again, if you have a polyatomic ion, you guys don't mess with the name. All right. Then I have, write the formulas for the following. Remember when you do formulas, Ca, write the symbol, put the charges in, +2, and then hydroxide's OH and it's -2. Okay. So, -1, excuse me. So they don't match up, so I have to crisscross them. All right. So 2 here, -1 here, crisscross them. If you have a polyatomic ion and you need more than one, make sure you put in parentheses. All right. Okay, silver sulfate, same deal. Silver is 1, sulfate is -2, so put the 2 by them. Don't put them straight down, put them across. Okay, nickel 3 bromide, nickel would be 3, bromide is 1, so NiBr3. Okay, sodium is Na, phosphide is phosphorus, because it ends in IDE, so I know it's an element. So I would just put the 3 there. Okay, chromium 2 iodide, Cri2. All right. And magnesium cyanide. Cyanide is a polyatomic ion. It has a -1 charge. Magnesium's 2. And again, you can go back through these. I will put this on without me babbling, so you can spend more time on it if you want. Okay. When we do molecular compounds, how do I know it's a molecular compound? It's made up of 2 non-metals. Okay. An ionic compound is a metal and a non-metal, or a polyatomic ion. Okay. So all you have to do for these is 2F. So that would be difluorine, pentaoxide. Make sure you have those, 1 is mono, 2 is di, and so on written down so you have them in front of you. Okay. Same with that one. That would be trinitrogen, and then heptachloride. Okay. So you just use those prefixes. CO2 would be carbon dioxide. The second one has to have a prefix. If there's only one, you have to use mono. The first one, if there's only one, you don't have to use mono. You don't have to say mono carbon dioxide. Just the second one, if there's only one. Okay, BF3 would be boron trifluoride. And again, you can go back and look at these, you guys. I'm just about out of time, so I'm trying to finish. Okay, I did finish. Okay, so make sure you go through this review, have your periodic tables, and call me or text or email me if you have questions. Good luck.